One thing biological systems are very good at is deriving novel goals. If you can't reach your original goal, come up with a new goal. What I'm showing you here is this little creature. It looks like a primitive organism I got from the bottom of a pond somewhere. It has these little hairs on the outside surface. They're cilia, and that's how this little guy moves around. You might guess that it's a primitive organism with a primitive genome. If you were to sequence the genome, what you would find is 100% Homo sapiens, unedited human genome. This comes from adult cells, from adult patients, taken from tracheal epithelia. When extracted from the patient, these cells self-assemble into this little self-motile little living creature, which has a lifestyle completely different from that of the human that it came from. It looks like no stage of normal human development. It expresses about 9,000 genes, in other words, half the genome, differently than the way it did when it was in the body. It has 4 specific behaviors that it can do, and you can build a little ethogram of it. One cool trick that they can do, if you plate a cluster of human neurons here and put a big scratch through it, they will assemble into something we call a superbot. So there's, I don't know, about a dozen of these things lit together. And what you can see is that over about 4 days, they knit together across the gap. They heal the neural wound. So who would have thought that your tracheal epithelial cells have the ability to make a self-motile little creature that also can heal your neural wounds? So lots of biomedical implications here, but fundamentally what you're seeing is that an unedited genome, just the cells themselves, if they can't do the normal thing that they do in the body, they will find something else to do, and often it is quite coherent and quite remarkably complex. So fundamentally in our group, what we've been studying is the ability of networks of living cells to use various principles that are now studied in machine learning and computational psychiatry and things like that, to create networks that actually interpret the information they're receiving from the genome. Not follow it as a mechanical device, but actually creatively interpret them as cues. And this bow tie that occurs when individuals compress down everything that the lineage has learned over the evolutionary time into a single generative seed, like an egg, and then it has to be creatively reinterpreted during morphogenesis, maybe as the normal embryo, but maybe like an anthrobot or like many other things. So we really have to ask, what really underlies the ability of groups of cells to remember their goals? What allows them to reduce the delta between what's going on now and what they think is the target? What allows them to interpret this information, this environmental and genetic information, creatively to solve novel problems? What's the machinery that does it?